Hello, my name is Andrei Apostol, and today I'd like to present to you FlipOut, uncovering redundant weights via sign flips, a work which I've done together with Maarten Stol and Dr. Patrick Forré as a joint project between the University of Amsterdam and Brain Creators. So, onto the introduction. As you may already know, there's a trend in deep learning to increase the size of neural networks, and while this strategy has been proven successful, it has drawbacks. For instance, applications that require real-time inferencing are difficult to tackle, and deployment on resource-constrained devices becomes impractical, as well as the fact that CO2 emissions from training and inferencing are reaching alarming rates. And pruning can help alleviate all these problems, but so we've noted 4 problems that are commonly plaguing pruning methods, namely the fact that they're either computationally intractable, they need to be retrained until convergence multiple times, they have a requirement for extensive hyperparameter tuning, and being unable to directly target a final sparsity. As such, we take a look at magnitude pruning, a popular method whereby the weights with the lowest magnitude at convergence are removed, with the idea that they have locally optimal points close to 0 anyway. And this process can be repeated in a train, prune, and fine-tune pipeline. However, there's problems with this, so detecting such weights, of course, requires the network to reach convergence. And if we perform this method iteratively, then we need to retrain the network again after each round of pruning. As such, detecting these weights earlier would allow for pruning to be applied during training, and even potentially remove the requirement for retraining altogether. And this forms the basis of our research topics, which is, can a heuristic for determining if a point represents a local optimum for a weight during training successfully be applied to pruning? And if so, is it possible to design such a method to avoid all the aforementioned issues? And onto our method. So recall that SGD computes the gradient over a mini-batch and updates the weights in the opposite direction. As such, the possible values of a weight after an update can be seen as being split into 2 regions. So here the dotted line is a point of local optimum, and depending on where the weight gets updated, which here is the yellow dot, so the yellow dot is the weight theta j at time step t. Depending on how it gets updated, it can either overshoot, which is the blue dot, or undershoot, which is the green dot. So with the behavior of weights when around local optima, we can construct a heuristic to determine if a point is a local optimum for a weight. This method, which we coined the aim test, goes as follows. For a weight theta j, we pick a value phi j at which we conduct the test. We train the model as normal, we record the number of over and undershooting, and if this number exceeds the threshold kappa, we can conclude that phi j is a local optimum for theta j. And using this for pruning, we can simply apply it at 0, and when we do so, overshooting becomes equivalent to a weight flipping its sign, and undershooting is equivalent to a weight getting updated to a smaller magnitude but maintaining its signs. There's a problem with this, however, so when we test at a value which is not a true local optimum, in this case the dotted line, observations of under or overshooting can simply be a side effect of the weight getting updated to an actual local optimum. In this case, for instance, the red dot is a true local optimum, and we record undershooting with respect to the dotted line regardless of how the weight gets updated to its true optimum. And we can have the same situation in reverse, where we observe overshooting. And we call these occurrences deceitful shots because they lead to the aim test concluding that the dotted line is a local optimum when in fact it is not. And we propose 2 methods of dealing with deceitful shots. So the first one is to take into account the distance from the weight to the tested value. So the number of occurrences could, for instance, be weighed by this quantity. And the second one is to ignore updates which are not in the vicinity of the optimum. And the second observation also allows us to simplify the aim test. How exactly? Well, with sufficient perturbation, undershooting can be converted to overshooting. As such, if we have such a perturbation injected, checking for overshooting becomes sufficient. And this can also be seen as restricting the aim test to a boundary around the tested value. So we perturb the weights by an epsilon, and here the purple interval around the tested value is of plus minus epsilon, and when the weight undershoots and lands in the interval around the tested value, so here the green dot goes to yellow, we add perturbation and it goes to the blue dot, causing an overshoot. Conversely, if we test at a value that is not a true local optimum, no interaction is going to be recorded in this case, since the weight doesn't lie in the interval. So with weight perturbation and ignoring undershooting, we can simultaneously make the aim test simpler and also reduce the number of deceitful shots. So with this in mind, we can now perform pruning by simply applying the aim test at 0 for all weights simultaneously. And we frame this as a saliency criterion. So the saliency of a weight is defined simply as its magnitude divided by the number of sign flips that it has undergone during training. And here we add a hyperparameter p, which controls how much we weigh the magnitude of the weight when computing this quantity. So now, by pruning periodically throughout training, we can directly select the final sparsity. So given R, the pruning rate, and M, the number of times that we prune, the sparsity of the network can be computed using this simple formula. So earlier we discussed that adding a perturbation to a weight can simplify the aim test, and we propose adding such perturbation through gradient noise. Specifically, we sample from a Gaussian distribution of mean 0, and whose variance is equal to the L2 norm of each layer divided by its dimensionality. So note that usually when adding gradient noise, we should reduce the amount of noise we add in later stages in training so that the network can reach convergence. And while other works do this with annealing schedule, this is not required in our case, since by pruning, we implicitly reduce the L2 norm of each layer while the denominator stays constant. So this induces an automatic annealing schedule. We only add a single hyperparameter here, which is lambda in the first line, which scales the amount of noise that we add. So now for our experimental setup. So we compare our methods to 3 baselines from literature: magnitude pruning, Hoyer square, and SNP, and random pruning as well for control. And we apply these methods to 3 networks: Resnet 18, VGG19, and DenseNet 121. As a metric, we use the trade-off between sparsity and accuracy, and whenever possible, we use an equal training budget, equal sparsity levels, and we keep the pruning rates and prune frequencies fixed. Also, we keep the training parameters fixed across these methods. So now for the results. So first, we perform a hyperparameter sweep for the 2 hyperparameters of our method, namely lambda and p, at 2 levels of sparsity. So starting with lambda, which scales the noise, we compare it to the optimal value. We compare the optimal value of lambda found by grid search to a default value of lambda equals 1. And for a low level of sparsity, the differences are negligible. When we increase the level of sparsity, the gap becomes larger. However, it is still within a reasonable distance. So for our subsequent experiments, we pick lambda equals 1 as a default value. We repeat these tests for p for 5 values, and we notice that p equals 2 is optimal in almost all cases, with a single exception for Resnet 18, at which the difference is about 1% at a high level of sparsity. So again, we use p equals 2 as a default value. Compared to the baseline methods, FlipOut has competitive results for low levels of sparsity, and also obtains state-of-the-art performance for the 2 highest levels of sparsity tested here. And this is for Resnet 18. On VGG19, the gap is even larger at the highest level of sparsity, so the story is kind of similar. However, it is interesting to note that FlipOut manages to obtain a drop of only 6 percentage points when only 0.1% of the weights remain when compared to the unpruned network, which is the dotted line in this plot. For DenseNet, FlipOut still manages to beat global magnitude at the highest level of sparsity, but generally Hoyer square is Pareto dominant in this case. So this brings us to our discussion. So to recap what we have presented so far, we've introduced the aim test, a method for detecting if a point represents a local optimum for a weight before the network has reached convergence. We've shown how to improve the aim test by dealing with deceitful shots via gradient noise and also taking the distance into account when computing saliencies. We've introduced FlipOut, which is an application of the aim test for all weights at 0 with the purpose of pruning. We've run experiments on a set of common vision models and datasets and have had favorable results. And for some practical considerations, we note that FlipOut has several desirable properties. It is computationally tractable. It does not require retraining by design. It does not need extensive hyperparameter tuning due to having strong default values. It can select a final sparsity directly. It is also competitive with other baselines found in literature. And I would also like to add that it is easy to implement. So all of these factors, when brought together, means that the user does not have to spend a lot of effort when extending this method to new datasets or new tasks. And with this, I would like to thank you for your attention and conclude my presentation.